All right, we're going to continue with part 2 of these notes of chapter 5, section 1. Today we're going to be solving some equations by using the one-to-one property. All right, so we're going to be solving some equations in this lesson by using what we call the one-to-one property. And essentially what we're saying in the one-to-one property is that if you have two exponential expressions, say, equal to each other that have the same base, then their exponents are going to be equal. Right, and then we can do the same thing in the other direction too. If I have two expressions set equal to each other and their exponents are the same, then I know that the bases are going to be the same. Right, so just some quick examples right here. If I have something like 2 to the third power is going to equal 2 to the x power, notice that the base in both of these numbers, or both of these expressions, is 2. If they both have a base of 2, essentially what we can do is sort of cancel out the bases, and then you end up with an equation 3 equals x. All right? Something similar that you could do, and you might see later on in this lesson, is you might have a base. I might have a to the power of 2, and this is going to equal, I'm going to say maybe 5 to the power of 2, right? These are two expressions that are set equal to each other. Notice that they have the same exact exponent. So essentially what we can do, sort of cancel out the exponents, and then you're left with an expression of a equals 5. All right, so it works both ways. Majority of examples that we're going to do, we're going to be given something. We're not going to be handed it to us, right? Something like this, right? I gave you guys pretty basic examples. Just so that you guys can kind of get the idea, but we're going to be doing some examples where we can at least rewrite an expression to have the same base as the other side of the equal sign, right? So again, it's not going to be as basic as these examples that I just gave you guys, but hopefully you'll see pretty quickly, hopefully you catch on to what we have to do to solve these kinds of problems. All right, so this is an example of an equation. All right, so look at number 15. This is an example of an equation where we can use the one-to-one property. Notice on one of these I have an exponent. On the other one I do not. Right? 3 has an exponent of x plus 1. 9 doesn't have any exponent. But we can rewrite this equation so that they have the same base. Right? If you look at 9, right, 9 you can rewrite to have a base of 3. So ask yourself, can I write 9 another way so that it can look like 3 to some power? And it can, right? 3 to the power of 2 is going to get you 9, right? So we get 3 to the power of 2 is going to equal 3 to the x plus 1. That one doesn't change at all. Now that we have the same base, we can cancel these out. And then you're left with 2 equals x plus 1, right? So set the exponents equal to each other, all right? And then all you have to do is some simple algebra. Just subtract the 1 on both sides, and you get x equals 1. All right. So again, this is a pretty basic example to start with, but it gets the idea across, right? So always change the base. Make sure that you have the same base before you start canceling things out. And then once you have the same base, cancel them out, set the exponents equal to each other. All right, so let's look at number 17. I'm going to do 16 in a minute, but first I'll try 17 because it's similar to what we just did. All right, 17. I have an 8 on one side, and I have a 2 to the 2x minus 1 on the other. I see a 2 here, and I see an 8 here, right? So I like to go from the bigger number to the smaller one. So can you change 8 to have a base of 2? And the answer is yes, right? 8 can be written as 2 to the power of 3. So in this equation, I can rewrite it as 2 to the power of 3 equals 2 to the 2x minus 1. And now that they have the same base, you can cancel out the bases and set the exponents equal to each other. So I get 3 equals 2x minus 1. And then just solve this simple equation for x, right? We can add 1 to both sides, and we get 4 equals 2x. And then divide both sides by 2. So we get x equals 2. All right, hopefully we get the idea. Something like number 16, right? I said we'd go back to this one. Something like number 16. Notice that we have a fraction. A lot of you are not big fans of fractions, so we can get rid of the fraction by changing our exponent, right? Remember, using exponents, you can change a fraction to its reciprocal just by changing the sign, right? So we have a negative x, and then what that's going to do is it's going to flip my 1 over 2, and it's going to make it 2 over 1. So I get 2 to the negative x is going to equal 8, right? But again, I can rewrite 8 to have a base of 2, right? Now I have a base of 2 over here. 8 can become 2 to the power of 3, and then these 2's can cancel, and then you get negative x equals 3. And then you can just divide both sides by negative 1, and then you get x is negative 3. All right, first 3 examples, hopefully not too difficult. All right, so 18 and 19, we could do something similar to what we just did, right? If you don't like the fraction, you can get rid of it, right? So we can go ahead and change this 1/3, right? Flip it just by changing the sign of our exponent. Right, so this negative x becomes a positive x, so we get a positive x to the power, that's, 3 to the power of x is what this becomes, right? We flip the base and then change the sign of the exponent. And 27 we can rewrite, right? 27 with a base of 3 is going to be 3 to the power of 3. So we have the same base, cancel them out, and so we get x equals 3. All right, same thing with number 19, right? If you don't like the fraction, flip it, right? So it becomes 3, and then you can change the sign of your exponent, 3 to the negative x. And then 81 can be rewritten as a base of 3, right? And it's going to be 3 to the power of 4, right? So cancel out your bases, and then you get negative x equals 4. Divide both sides by negative 1, and you get x is negative 4. All right, so maybe the hardest part of these kinds of problems is figuring out which base to use. It's not going to be anything super crazy, right? All of these you can kind of predict what the base should be, right? So something like number 20, even though 20 looks a little bit different than all the ones that we've done before, let's still apply the same idea, right? I want to get the same base. So here I have a base of 2, and here I have a base of 8, right? 8 I know is 2 cubed. Right, so I can leave this side alone, 2 to the x plus 4, that's fine. But then 8, I can rewrite that as 2 to the 3rd to the power of x minus 6, right? This whole thing right here became this whole thing right here. All right, but remember, if we have a power to a power, we want to multiply the powers, right? So if I have 2 to the 3 to the x minus 6, I'm going to distribute that 3 to the x minus 6. And then you get 2 to the x plus 4 is going to equal 2 to the 3x minus 6, or minus 18, sorry. All right, go ahead and cancel the bases because now their bases are the same. And you get x plus 4 equals 3x minus 18. We can subtract 3x on both sides. Subtract 4 on both sides. And then you get negative 2x is equal to negative 22. And then divide both sides by negative 2. And so you get x is 11. All right, some more pretty simple examples. All right, so something like this one right here. 2 to the 3 minus x equals 8. I know that 8, we can rewrite that as 2 to the power of 3. And then on the other side, I still have a 2 to the 3 minus x. The 2's are going to cancel out. And so we get a 3 minus x equals 3. All right, and then you can subtract 3 on both sides. We get negative x is 0, and then if you divide by negative 1, you get 0 divided by negative 1, which is still going to get you a 0, right? In any of these problems, if you ever are unsure of the answer that you get, you can always plug it back into the original equation and see what you get, right? If you plug in 0 here, right, I'll just check it right here. You don't have to check it, but just in case maybe you have doubts about your answer, we get 2 to the 3 minus 0, right, because x is 0, equals 8. And let's see if this is true, right? 2 to the 3 minus 0 is just 2 to the 3rd, and 2 to the 3rd is indeed 8, right? So we get 8 equals 8. This is true, so it works. All right, so that's just if you have doubts. Again, you don't have to do it every time. But just in case, that's one way to check your answer. All right, the next one, same thing. 25, I can change to have a base of 5. So you get 5 to the 2x plus 1 equals 5 squared. Cancel out your 5s, and you get 2x plus 1 equals 2. All right, now we can subtract 1 on both sides, and we get 2x equals 1. Divide both sides by 2, and we get x equals 1/2. Oh, wait, hang on. Okay. This next one, I didn't go into too much detail about e yet, but what I did say was you can treat it just like any other number, right? E is a number. It gets you that 2.718 constant. So what you can do is simplify these. Make sure these are both fully simplified. E to the 4x minus 1, there's nothing more you could do to that. Right, but e to the 2 to the x, power to a power you multiply. So we get this equals e to the 2x. Cancel out your bases, and you get 4x minus 1 equals 2x. We can subtract 4x on both sides, and we get negative 1 equals negative 2x. Divide by negative 2, and we get x is 1/2. All right, so again, e, just treat it like any other number. If it's the same base, just cancel it out, solve whatever's left over. All right, let's keep going with some examples. In this one, number 24, 27 and 9, you can't really change them to get the same base as the other one. But you can change both of them to have the same base, right? So 27 and 9 both can be written to have a base of 3. So 27, you can write that as 3 to the power of 3. And then this is to the power of 4x. And this is going to equal 9, which we can write as 3 to the power of 2. And this is to the power of x plus 1. And then power to a power, you can multiply, so we get 3 to the 12x is going to equal, you can multiply this one as well, right? 2 times x plus 1, power to a power. We get 3 to the 2x plus 2. And then now we have the same base. So you can cancel, and then you're left with 12x equals 2x plus 2. You can subtract 2x on both sides to get the x by itself, and then you get 10x equals 2. Divide both sides by 10, and you get x equals 2 divided by 10 is going to get you 1/5, right? Simplify fully. All right. And then same thing with this next one. Just rewrite to get the same base. 4 can be written to have a base of 2. So 4, I'm going to rewrite that as 2 to the power of 2. And this is all to the power of x minus 2. And this is going to equal 2 to the 3x plus 3. And then power to a power, you can multiply the powers. You get 2 to the 2x minus 4 is going to equal 2 to the 3x plus 3. And then now we have the same base. Cancel them out, and you get 2x minus 4 equals 3x plus 3. All right, I'm going to add 4 on both sides. You can subtract 3x on both sides. And so we get negative x is positive 7. And then so if we get a positive x, we can divide by negative 1 on both sides, and you get x equals negative 7. All right. And then 26 looks a little bit different, but again, e, treat it just like any other number. If I have a base of e, rewrite them so that they both have a base of e. They do, right? But I want them to look like each other. So one thing that you could do is, if you don't like the way that it's written with the fraction, you can change it to not be a fraction, right? So e, you can bring from the bottom to the top by changing the sign of this exponent, right? So it becomes e to the positive x is going to equal, same thing here, right? If I have e to the positive 2, I can make that a negative 2 and bring it to the top. Equals e to the negative 2 to the x plus 1. All right, and now I get e out of that denominator, and you can now distribute negative 2. All right, so we get e to the x equals e to the negative 2x minus 2. And now we have a base of e, so we can cancel it out, and you get x equals negative 2x minus 2. Right, and you can add 2x on both sides, and you get 3x equals negative 2. divide both sides by 3, and you get x equals negative 2/3. All right, last few examples. These ones are a little bit more challenging, but not really, right? They're just a little bit different, right, than the things that we've done before. This one, number 27, if I have the square root of 2 to the x plus 4 equals 4x, I had asked in class, how would you go about doing this one? A lot of you said that you would square both sides, which isn't a bad idea. It's just a lot of you might get confused after that step of what to do, right? So what I would do instead is I would change square root of 2, right? Remember this square root way back in first quarter, right? Beginning of first quarter, we said that square root of 2 can be written as 2 to the power of 1/2, right? Remember that radical, that square root is the same as a fraction in the exponent. So we get 2 to the 1/2 to the power of x plus 4 is going to equal, and then 4x, this one we can simply change to have a base of 2. So we get 2 to the power of 2 to the power of x. And now we wrote these to have a base of 2. So I can go ahead and use power to a power to multiply. And then I get 1/2 times x. So I get 2 to the 1/2 x. And then 1/2 times 4 is going to get you 2. Right, and this equals 2 to the 2 times x is going to get you 2 to the 2x. And now we can go ahead and cancel out our bases, and we got 1/2 x plus 2 is going to equal 2x. All right, and then from here you would get x on one side, your constant on the other. If you don't like that fraction, though, if you don't want to do 2x minus 1/2 x, right, we learned back in chapter 1, right, beginning of chapter 1, that to get rid of a fraction, you can multiply by the denominator, right? If you multiply by a common denominator, that just gets rid of your fraction. So I'm going to multiply everything by 2 because that's what I see in the denominator. And then 1/2 is going to cancel out with the 2, and I just get x. And then everything else just gets multiplied by 2. X plus 4 equals 4x. And then you can subtract x on both sides, and we get 4 equals 3x. Divide both sides by 3, and you get x equals 4/3. All right, now something like number 28. This one's a little bit different because now we're looking for the base. I'm not looking for the exponent. We already know the exponent. I'm looking for the base, b, right? So what we can do is we can still do the same thing that we've done before, try to get one side to look like the other. So what I'm going to do is I'm going to change b to the negative 3, right? If you don't like that negative in the exponent, you can change it to a positive by moving it to the bottom, right? So we get 1 over 27 is going to equal 1 over b to the 3rd power. And then notice the top on both of these is 1. On the bottom, I have a 27 and a b to the 3rd power. I can just set the bottom equal to the bottom. All right, so we get 27 equals b to the 3rd power. And you can go about this two ways. You can treat this just like a cubic equation and try to get the b by itself by cube rooting. Or you can do it the way that we've been doing it before and change 27 to have an exponent of 3. We can write 27 to be 3 to the power of 3, and this is going to equal b to the power of 3. And because of our one-to-one property, we can cancel out our exponents, right? Before we've been canceling out our bases, but it works the same way with exponents. If you have the same exponents, you can cancel it out, and then you just get b equals 3, right? And you can always verify and plug it back in to check and make sure that your answer is accurate. All right. Now 29 is something similar. I'm looking for the base. I don't know. I do know the exponent. I don't know the base, right? And there's no way that we can write 4 to look like a base of r. So what we can do instead is get the r by itself. Another old concept, right, from chapter 1 is to solve a radical equation, right, or an equation that has a fraction as the exponent, is to raise both sides to the reciprocal. So I can raise both sides to the 3 halves, and that's going to cancel out the 2/3, right? But a lot of you maybe wouldn't think to do that, right? So what I would do instead, all right, 4 equals, okay, I'll do it this way. A lot of you might think to do instead is to do it one step at a time, right? If you see the bottom is 3, you can start by raising both sides to the power of 3, and then this 3 cancels with this 3, so we get 4 to the third. That's going to get us 64 equals r to the second, right? The 3 and the 3 cancel out. And then from here, you can square root both sides, and then you get 8 equals r. All right. Same thing if you were to do it this way up here, right? You just might, I think a lot of you maybe will get confused at some of the steps. Another thing, I believe someone asked in class, why is this not plus or minus 8, right? It's not plus or minus 8, even though they do satisfy this equation. But remember, in the very beginning of this lesson, we had defined an exponential function to have a positive base. Remember, a is greater than 0, and a cannot equal 1, right? These were our 2 restrictions, right? So if a has to be a positive number, then I can't have negative 8 as a solution. All right, and that completes this lesson. This page has some of the harder examples, but the idea is still the same in all of them, right? So this covers your one-to-one property, and then in the next lesson we're going to teach, we're doing compound interest, and I'm going to go into a little more detail about the constant e.